Hello and good day, doctor. My name is Amizhdhan BALAKRISHNAN, and today I'll be presenting about my lab 4, which is Laplace transform. So my matrix number is 231363008, and today I'll be presenting about question 4.1, and as you can see this is the coding and this is the question. So I'll straightforward go to the MATLAB code. As you can see here, this is the code. Okay, so I'll start with the sorry. So I'll be demonstrating about my MATLAB online code for computing the inverse Laplace transform and performing partial fraction expansion. This is the key topic in engineering mathematics, especially useful for solving differential equation and analyzing system responses. As you can see here, this is the part. So first I begin by clearing the MATLAB workspace using clear and CLC. This ensures that there are no old variable or outputs interfering with my current session. Next I declare as a symbolic variable using SMS. This allows us to work with Laplace domain expression symbolically. As you can see here, I have declared variables, and for this one Fs represents a transfer function or Laplace expression that we want to invert back to the time domain. To compute inverse Laplace transform, I use eLaplace Fs and assign the result to Ft, which is here. Then I use pretty Ft to display the time domain function in a more readable form, which is this one. Then next I perform a partial fraction expansion. First I define the number and denominator coefficient as a vector, which is this one, partial fraction. This represents the same rational function as Fs, but now in numeric form, suitable for control systems or signals processing application. Using Tf denominator, which is this one, I convert it into a transfer function format and assign it to variable x. Okay, so as you can see here, this one, I use the residue function to get the partial fraction expansion where R contains the residues, P to pole and K direct terms. For this polynomial coefficient, finally I convert the transfer function into its zero pole gain form using the ZPK function. This form is useful in control system analysis because it clearly shows the system zero poles and overall gain. And for this one, the one I was explaining, zero pole gain. So if I run the code, this is the output I'll be getting. Fs, this one, sorry, this one. As just now I said the transfer function, the continuous time function, and this is the for the zero pole gain model. Okay, for the next question, which is question 4.2, 4.2a. This is the question and this is the code. So I'll straight away show you in the MATLAB. As you see here, I'll straightforward run for you first. So if you run the code, you'll be getting this output and this. First I'll explain. Okay, as I said beginner just now, I began by clearing the workspace using clear and CLC to ensure a clean section. Okay, for the numerator denominator, I define the numerator and denominator of the transfer function. These are entered as vectors representing polynomial coefficients. This is the numerator and this is the denominator. This corresponds to the rational function x as equals to s3 plus 1 and that. So for this I created a transfer function using the MATLAB TF function, which turns the coefficient into a system representation. For this one, partial fraction using residue. So function to break the transfer function into its partial fraction. This is useful for analyzing the time dominant behavior of the system. So for this one, the zero pole gain form, I convert the system into its zero pole gain form using the ZPK function. This makes it easier to the system's behavior at a glance. This represent helps when designing controllers or analyzing stability. So for this one, plot the zero pole map. I visualize the pole zero distribution using the PZMap function. This plot is useful to determine system stability and resonance. Finally, I use the plot magnitude response function to plot the frequency response of the system. This plot shows how the system responds at different frequencies. So I've created a transfer function, perform partial fraction expansion, converted into a zero pole gain form, and visualize the system using the pole 0 and both plot. So this is the output I got. This is the pole 0 map of axis, and this is the magnitude response of it. So I will be having two figures. So thank you for watching my presentation. I hope this helped demonstrate how MATLAB can be used and to analyze and understand linear system effectively. Thank you so much.